Okay, so in terms of midterm coverage, all tutorial questions up until and including today are all fair game. So this will end all of the amplitude modulation questions you will see for the midterm. Okay, so this is there's 3 questions. It shouldn't take very long. Hopefully 20 minutes tops, maybe half an hour if I do make mistakes. But here we go. So the first question involves this block diagram. So we've got a baseband signal, okay, with a Fourier transform. The spectrum looks like the following here. This is in terms of omega, all right? So also note that this is with respect to times 2 pi. So this is actually, so these things are all going to be multiplied by 2 pi. So this is 2 pi b and then pi b and so on and so forth. Okay? So we have this block diagram, and the purpose of this question is to take a look at the spectrum of the Fourier transform at each point in this block diagram. So we're going to take a look at the spectrums at points A, B, C, and D. Okay, so this actually generates a single sideband signal. So we're going to explore that in more detail. So this block diagram, HT, stands for the Hilbert transformer. So this means that for frequencies that are greater than 0, you multiply by minus j. So the Hilbert transformer is such that you multiply by j when your frequencies are positive and minus j when your frequency, no, so it's minus and plus when your frequencies are negative. Okay? So the first question, the first part is compute and plot the spectrum at points A, B, C, and D. Okay, so without further ado, I'm going to call this point M sub A of t, M sub B of t, M sub C of t, and M sub D of t. So each of these points I'm going to denote as a time domain signal and its corresponding frequency domain signal. Okay, so A. MA of t is simply the message signal that's coming in multiplied by sine. So the sine, it's not sine, it's not cos, it's sine now. So that makes it a little more difficult to deal with. I'm just going to call this omega ct because I can't keep writing 2 pi fc. So omega c we know is 2 pi fc. Okay? So when I take the Fourier transform of this, okay, we're going to do this in terms of omega, all right? Okay, so if you remember your Fourier transform properties, this is equal to 1 over 2j, and then m of, let's see here, so 1 over 2j m of omega minus omega c, and then minus 1 over 2j m of omega plus omega c. So this deals with convolution, okay? So this just, you're just so instead of half, it's half 2j, and then what I'll do is I'm going to simplify this. I don't like the j's on the bottom. So what I'm going to do is remember that 1 over j is equal to minus j. Okay, so if I take this and I put this into here and here, then what you're going to get is j over 2 m of omega plus omega c, and then minus 1, or sorry, j over 2 again, m of omega minus omega c. Okay, so that's what's happening here. So the Fourier transform of this, okay, is simply going to, let's see here, not A, yes, A is fine. So what you're simply doing is you are just going to, let's see, yeah, so you're going to take copies of the spectrum and then you're going to basically just multiply by j over 2, all right? So let's see here, so frequency and then Hilbert transformer, okay. So that's what it's going to look like. So basically what your spectrum is going to look like, okay, is the following. So notice that we have copies of, you know, this here, right? So this will be omega times 2 pi. I don't want to, you know, it's technically going to be 2 pi b and all that, but omega times 2 pi. Okay? So you're going to have 2 copies, one at omega c and one at minus omega c, and they're going to be scaled differently. So j over 2. So what's going to happen is our spectrum here, okay, so minus b, so we have minus b, b over 2, plus b over 2, and plus b. Okay, so it's going to look like this between here and here. Okay, and then the height is j over 2, not j over 2. Sorry, it's minus. Okay, so you know I'm just going to put a height here. This is minus j over 2. Okay, technically it should go on the bottom, but I messed it up, so that's okay. So it's technically a minus here. Okay, and then you're going to have another copy over here. So minus omega c minus b, and then minus b over 2, and then plus b over 2, and plus b. So that's going to look like this. Here. and this is scaled by j over 2. So if you have an imaginary, amplitude, you can just put it right beside here. So technically this is a scale of 1/2, but then you can actually either draw it down below. You can do this if you want. That's totally, if you can do this and make this j over 2. Or you can have it on the top and then lose a minus. So either one is acceptable. So this or this is totally fine, whatever you want. As long as I can clearly see that there's a negative there. But either one is totally fine. So this is what the spectrum looks like for at least the first part. Okay? Now the next part's going to be a little more complicated. So at part B, okay, what's going on here is you have to put it through a Hilbert transformer. Okay? So what you're doing is basically, so what's happening, if you remember what the Hilbert transform looks like, this is for part B, you are basically multiplying any values that are negative by j and any values that are positive by minus j. Okay? So all you're doing now is any values that are negative, you multiply by j, and any values that are positive, you multiply by minus j. Okay? So what's going to happen here is that you get, let me see here. So remember, for m of a, right, we had this guy over here. Copy. So this is our expression. Okay? For m of b, right, as you can clearly see in the spectrum, this one deals with the negative side of things, and this one deals with the positive side of things. So if you use this guy, so any values that are negative, you multiply by minus j. Any values that are negative, you multiply by j. Any values that are positive, by minus j. So if you use this relationship, right, the first term gets multiplied by j, because these are going to be all negative. So you get j over 2, and omega plus omega c, okay? And then minus, then we have, let's see here, so anything's positive, right? So this becomes minus j over 2, m of omega minus omega c, okay? So remember, j squared becomes minus 1, so you get minus 1/2 m of omega plus omega c, okay? This and this become positive, but the j squared still becomes minus 1, right? So this becomes minus 1/2 m of omega minus omega c. So basically what you're going to do is you're going to take this one and just flip it so that they go all below, which are minus 1/2. That's all you're going to do, okay? So maybe it looks like this. So minus omega c b, and then this is b over 2 c. Okay, I'm going to change this, obviously. Okay, and then split this up. Actually, no. Yeah, okay. So we have omega c minus b, and then omega c minus b over 2. Okay, omega c, and then plus again. And then omega c is plus b. All right, so we have this, and then everything's going to be scaled down minus by minus half. So 1, 2, like that, and 2 like that. Okay, so that's what's happening here. So we have this one is over here, and this one is over here. So let's do it in a different color, just to make things look nice. Okay, that's point B. Okay, any questions here so far? You sure? Okay. Okay, part C now. Let's do part C. So part C is basically taking your signal and then doing a Hilbert transform outright. Okay. So this means that any values that are less than 0, you multiply by j. Any values that are bigger than 0, you multiply by minus j. Right? So for C, m of c of t, now we actually compute the spectrum, right? So it's going to look like this. So any values that are negative, right? Let me see here. So it's minus, and I'm trying to remember the minus and, yeah, so minus and plus, sorry. So minus. Okay? And any values that are positive, you multiply by j. Okay. So if you want to do this, if you actually want to represent this properly, you can kind of do it like this. So you have 1, 2, and then 3, 4, right? So this is omega c, omega c, not omega c, sorry, this is just b. We're doing baseband here, yeah? So, minus b over 2, 0, b over 2, and b. All right? So what's happening is 0. So this portion here, okay, this gets multiplied by minus j. All right? Ah. Okay. So this here, this gets multiplied by minus j, and this portion here gets multiplied by just j by itself. Okay, so that's what that spectrum looks like. Then finally, part D, you're just simply taking this and modulating again. All right, so m of d. Okay, so this is, so what you're doing is you're actually multiplying by a sign. Okay, so it's just going to be this relationship, but instead of m, it's going to be m of c. So you have j over 2, m of c, omega plus omega c, and then minus, and then it's m of c. Okay? So when you have this spectrum, it's going to look like this now. So, all right, so D. So it's going to look like this now. So you modulate over by minus plus omega c, okay? And then what's going to happen is that it's going to look like this. Okay, so what's actually happening is, okay, so let's actually draw the actual thing first. Sorry, let's just, okay, and then, okay, we'll leave it like that, and then this is, sorry, this is minus b plus b, okay, and I'll just leave that undetermined, so, okay, so you're going to take this, shift it to the left, okay, and then you're going to multiply by j. So one portion is going to be minus a half, the other portion is going to be positive a half. So this portion between here and here is scaled by 1 over 2, right? Because minus j times j over 2 becomes positive a half. And then this portion here gets scaled by minus, all right? This side, right, you get, so this side here, so this one's j over 2, right, so this way, so you have j times j over 2, and then you subtract, right? So what'll happen is that you get a positive, so this becomes 1/2 over here, and minus 1/2 over here. Okay, so, yeah, so let me see, j minus j, and then, sorry, we have a minus j here, so minus, sorry, it's minus, and, sorry, I flipped up, so it's minus and plus. Makes sense because it's got to be symmetric, right? So this is minus and plus, and then 1. Okay, so this is part D. If you want, you can flip it. If you wish, you can, draw something like this. You can go like this, and then it look like this, I guess. You can do that if you want. And then this would look like, this and that, if you wish. You can do it like that if you want. Doesn't matter. Okay, but either one is acceptable. And then you can have a half and then a minus half here. Okay, so finally, we take a look at so we have parts D and D, and then compute and plot the spectrum of MS. So what you have to do now is you have to do this part. So it's taking B, D, and subtracting B, okay? So that's the next part. So the single sideband modulated signal in terms of omega, okay? Basically what you're doing is you're taking D and subtracting with B, okay? Now if you do that, so this is D here, and then this is B from above, right? What's happening here is that if you subtract these two signals, right? So what'll happen is that, let's see, what's going on here. So if I take D and I subtract with B, okay, what's going to happen is that these two halves, these two halves on the left halves are going to cancel, right? So you have this guy and this guy, they're going to cancel with each other. And then you're left with these two here by themselves. So what's going to happen is that you're just going to have this instead. So you're going to have this here and this here. So if you actually do it, go ahead and you actually subtract one with the other, they will actually cancel out. So we actually just get this one over here. Actually, I think I flipped these. Give me a moment. Okay, you know what you know what I did? Okay, I flipped these. So this is minus and this is plus, and this is plus and minus. Sorry about that. So actually what's going to look like, it's going to look like this. I did the math wrong, but it should look like this. Okay, and then let's see here. So we have like that. Okay? And then when you subtract these two things together, you will end up with this. And then this is scaled by a factor of 1. Okay, so that's what it looks like. And then you have omega c, and then omega c plus b. And then this is omega c, and then omega c plus b. All right, so that's what that looks like. Sorry, it took a little long there. Okay. All right, so that's what we got there. So show how to recover your baseband signal from a single sideband. That's actually very easy, okay? The next part, all you have to do is just use a coherent detector. So if your single sideband's coming in, right, you just multiply. We're going to use a factor of 2 here, okay? So you put a low-pass filter, and then you get the actual output, okay? Which actually makes sense. You can go ahead and try that if you wish. So if you were to multiply by 2 cos, what's going to happen is that you're going to get 2 copies that are shifted to the left and to the right, okay? So what will happen is that you're going to get 1 copy, which is over here, right? This is B, and this is omega C, and then this is, not omega C, but yeah, it's shifted over. So this becomes 2 omega C and 2 omega C plus B, right? And then you get 1 more copy over here. So you get, let's see here. So we got 1 here, right? And then another one over here like that. And this is minus 2 omega C, and then this is minus 2 omega C plus B, okay? And then when you apply a low-pass filter, so this is between minus B and B, you apply a low-pass filter, you get that, and then that's gone. Okay? So that's how you do it. Times 2 pi. And that's it. Okay, so that's what you do. You just do a coherent detection, do a low-pass filter, and then that's what you get. All right? Okay. Any questions here? Yeah, that was actually a pretty hard question to do. The rest of them should be a joke now. Okay, so this one's going to be more sketching, and the last one's just going to be sketching as well. Should be very simple. Okay, this is question 2. Okay, I'm halfway through. I'm almost done, guys. So the following figure shows a block diagram of a 2-stage single sideband modulator. Okay, so what's happening here is that you modulate with a cosine, do a bandpass filter, apply it again, do it with the cosine, and notice that these 2 frequencies are different. Put another bandpass filter, and you get an output, and then this will give you a single sideband modulated signal. So the input spectrum has a frequency hole between 0 and 0.5. So this is important here. Okay? So the next part of this question follows. All right. So the oscillator frequencies are 100 kilohertz and 9.9 megahertz. So this is 100 kilohertz and 9.9 megahertz. Okay? The bandpass filters are designed such that the output of the 2-stage modulator is just the upper sideband of each. So this means that after you put this through your bandpass filter, you only capture the upper sideband. So that's exactly what that means. So you're just getting the upper sideband. So we need to sketch what the signals look like at all the nodes, figure out what bandpass filter you need for each of them, the stop band and the pass band edges, and talk about why exactly you want to use a 2-stage over just a 1-stage. All right, don't come so bad. Okay, so this is defined in terms of F, so we're going to practice in terms of F. Okay, so for A, okay, so at part A, okay, you're modulating by cosine. Okay, so that means that you basically, go plus minus the frequency, and then you have to scale by half. Okay, so I'm not going to compute the actual spectrum, so we can actually do this. So you multiply by a half, okay, and then you have 100. Okay, I'm going to do this in terms of kilohertz. Okay. So this is minus 100, okay? And then this is also in terms of kilohertz as well. So what's going to happen is that, you plus minus, so this becomes 100.5. This is 99.5, and this is 104, and this is 96, okay? Because that's what's defined here. So it goes from 0 to 4, and then there's a 0.5. There's a gap in between 0 and 0.5. So it's going to look like this, okay? And then you're going to do the same thing on this side. So minus 104, minus 100.5, this is minus 99.5, and this is minus 96, okay? And it'll look like between here and here, and here, okay? This is F. And then this is at part A. I'm going to call this MA of omega, okay? So these are at the different stages. So this is A, okay? Now, when you apply your bandpass filter, it says that your bandpass filter should only keep the upper sideband. Okay, so the upper sideband is what? If you split this down the middle, the upper sideband is this guy over here, right? So the output will just simply just chop these off so that you're left with just the upper sideband. So let me just copy this. You know, it's great to copy things on a tablet. Okay, so in this case, this is part B. Come on. Okay. So this is part B. Okay, and then this is M of B omega. All right. So this is the portion at the output of the bandpass filter. Okay, upper sideband goes away, goes away, goes away. So you're left with just, that's it. Okay, so so this is the upper sideband now. Okay, so that's what's captured. This is after the bandpass filter. You only want to capture the upper sideband. Okay, now part C asks you to modulate by f of 2, which is 9.9 megahertz. All right, so now I'm going to change the scale to megahertz. So this here is the same as 0.1005 megahertz, and this is the same as 0.104 megahertz, and this is in kilohertz, okay? I'm just putting these down as a reference because when I change to megahertz, then you'll see where these numbers come from. Megahertz, all right, sorry. Okay, so now part C asks us to modulate one more time with a carrier frequency of 9.9 megahertz, okay? So now I'm going to put this in F, I'm going to do this in megahertz, all right? So my carrier is centered at 9.9, and this is minus 9.9, all right? And now what I need to do is I have to take this and I have to shift it left and right by this much, okay? So if, let me see here, so 9.9, so this is 9.9, all right? Then what's going to happen, so I need to shift this by 9.9. So at 9.9, right, that's the center, and then what will happen is that I'm going to have 9.9104. Yeah, so let me see here, 9.9, and then that's 10.04. So 104 kilohertz is 1, so 9.9. No. So if this is 9.9, okay, then what's going to happen is that this here is 9.9 plus 0.1005, which is 10.0005. Okay, so that's this portion here, and then this one here is going to be 9.9 plus 0.104, which is 10.004. All right, and then remember it's scaled by 1 over 4 because we had a 1 over half, then you have to do a 1 over 4 again because you're modulating again. Okay, so you have this guy, and then you also have another copy which is over here, this over here. Okay, and then you just simply subtract. So 9.9, in this case, you're going to have 9.8995, okay, and 9.8, I guess 9, whatever that is. I guess 9. Yeah, 9 points. Let me see here. So 9 point. So you're subtracting 0.005 and then 9.896. Yes. Okay. There we go. Okay. And then you do the same thing on this other side. So you have 1 here and then 1 here. Okay. You know, I'll skip labeling the negative, but you just have to apply the. I just want to get through these as quick as possible. So you know, this is what we have. All right. So that's this point, and then portion D, you're just simply doing a bandpass filter on this, right? So just take this guy, and then you want to capture the upper sideband only. So. Okay. So let me see here. So it would just be get rid of this and get rid of that. Okay. Okay. And that would be it. So that's part D, and then you still get a single sideband when you're done. Okay, so the next part says specify the filtering requirements and you know, the stop band edges and the pass band edges and so on and so forth. Okay, so they want us to design the right bandpass filters to do this. Okay, so let's actually take a look at part B again and part D again. So this is part B here. Okay, so I'm going to take this. I'm going to use this as a guide to help me design the right bandpass filter. All right, so let's put this here. Okay. So what you can actually do is you can actually make this non-ideal, right? What you can do is you can make it so that you have a transition band going up like this, and you can have a pass band like this, and then you can go down like that instead. So you can make this a non-ideal bandpass filter. So between here and here will be your transition bands. All right? And then you can make between here and here your stop bands. You can do the same thing on this side, right? So you can go from 100 to 104, and then down like that. Okay, so that's how you design, the first bandpass. It's nice because they say you have to design both stop and pass, which means that it's a non-ideal filter. And then you can do the same thing for this guy over here, right? So copy this. So that's MB. This would be your bandpass filter. This is BPF1. Okay, and then you do the same thing for BPF2. All right, so this is BPF2. Okay, and then, yeah, you guess you don't need that. You can leave it as a 1, I guess. Or what you can do is you can make the bandpass filter have a gain of 2, so that it cancels out the half every time you do it, but it's okay, we'll just do a 1 here like that. Okay, so in this case, what you can do is you can make it so that the transition band goes like this. There's a pass band and then a stop band like that. Okay, so this would be your pass band. Okay, between here and here, those are your stop bands, or not transition bands. Okay, and the same thing over here. Oh, I didn't label that, but it's just it would look like this. Pass here and then down. All right, whatever those numbers would be. Yes, sorry. Sorry, where? Oh, stop band. Yeah, just making sure you're paying attention. Pass bands. Yes. Fantastic. Good. Okay, and that's how you do it. So the next question says, discuss the main advantage of using a two-stage structure. Well, the reason why you use a two-stage structure is because it allows you to design bandpass filters that are non-ideal. So if you try to do it with one stage, it's going to be very difficult to be able to specify a bandpass filter that is realizable. Okay, so that's basically the only point you need to bring up. So part C, the advantages are that it allows for better reliability, I guess. Okay, and BPFs can be non-ideal, I guess. All right. Okay, guys, last question. I promise this one's going to be easy. This one's vestigial, so this actually is not a problem at all. This should be okay to do. Last question, then we'll get out of here. We should be able to get out of here within the next 5 or 10 minutes or so. So consider using a vestigial sideband modulation scheme where the message is a sum of 2 cosines. Okay, the first one is 50 hertz, and the second one is 150 hertz. So we're going to put it through a double sideband suppressed carrier here, and then you're going to apply a vestigial sideband bandpass filter to generate your vestigial sideband modulated output. Okay, so very simple. Now the questions are as follows. The frequency response of the vestigial sideband filter, we're only showing the positive only, okay, is the following here. So f of v is what's known as the vestigial frequency requirement. So it's here, and the bandwidth of this filter is 250 hertz, okay? And the carrier frequency is 10 kilohertz, all right? So what this is implying is that you're just on the positive side only, it's going to look like this. So we have 1, 0.5, and then here we're going to define this in terms of kilohertz. So this is 9.9, okay? And then right here is going to be 10, right? And right here will be 10.1. And over here is 10.25. Okay, because this is a thing of 250, right? Not 10.2, yeah, it's 10.250, yes, 10.25. All right? So that's what's happening over here. So 10.2, oh, so not 10, but it's 10.35, sorry. Right? Because if this is 10.1, you're adding another 250. So it's not 250, it's 250, sorry, it's 2.5. Sorry, it's plus B here. So it's 2.5 there. Okay, that's fine. So this is what the frequency, well, this is what the filter will look like. This is just positive only. So we have to figure out what the frequency, what the Fourier transform of the output will look like. Okay, so before we do that, okay, we know that the message signal, okay, is defined as what? It's so it's cos of 2 pi, and then the first one is 50, and then plus cos of 2 pi times 150. Okay? So the Fourier transform, they're dealing with this in f, which is fine. So this becomes a half delta f minus 50 plus delta f plus 50, and then another couple delta f plus 150 and minus plus 50, and this is plus 150. Okay. All right. So that's what we have, okay? So the transform is simply going to look like this. We have minus 150, we have 50, 50, and 150, and they're all scaled by 1/2, okay? Now, the output, after this point, we have to modulate it by 2 cos of 10k, okay? So after we do so this is after modulation, so when we modulate, come on, so when we modulate, so when you do m of t, cos of 2 pi times 10k, okay, what's going to happen is that the spectrum gets shifted left and right. And then because the impulses are scaled by 1/2, when you do this, when you find the Fourier transform of this guy, you're going to get scaled by a quarter, because 1/2 times 1/2 is a quarter, okay? And then what's going to happen is that we have 4 impulses left and right. Okay, 1, 2, 3, 4. So the carrier frequency is at 10 and 10, okay, and this is in kilohertz, okay? So this means that when we shift over, this becomes 10.05, and this becomes 10.15, this becomes 9.85, this becomes 9.95, right? And then you do the same thing on this side, 10.15 minus 10.05, right? And then minus 9.95 and minus 9.85. Okay, so this is what it looks like. Now all you have to do is you have to put it through a vestigial sideband. So let me copy this now, and then we're going to put it through this filter. So I'm going to have this here as a reference, okay? So if you take a look, this is linear. So in between 9.9 and 10, we have, this is 9.95, right? And right here is 10.05. So because this is linear, this is halfway, this becomes 1/4, and this becomes 3/4, okay? So what's going to happen is at this point, the output is equal to 1/4. So I need to scale this one by 1/4, okay? And then I need to take this guy over here. Come on, why don't you change the color? This guy over here, and I need to scale this by 3/4. Sorry, not that one, the other one. Oops. So this, I need to scale this one by 3/4. Okay? And then this one stays the same. It's just equal to multiply by 1, because 10.15 is right over here. So I don't have to change anything. Okay? But then this one goes away, because it's outside of that frequency response. So what's going to happen now is the spectrum is going to look like this. Okay? So it's going to look like this now. So we have 9.95, 10, 10.05, and 10.15. And then so 9.05, 15, come on. 1.5, and then minus 10.05, 10, and 9.95. Okay, so this is a quarter, and we have to scale by a quarter again. So this one will be 1/16. Okay, the one at 10, there's nothing, but at 10.05, it becomes 3/4 times a fourth, which becomes 3/16. So here becomes 3/16. And then this one at, 10, this is 10.05. And then at 10.15, it stays the same. It just stays at 1, so we actually get 1/4. Okay? And then you do the same thing on this side. So here, and then here, and here. Okay? So this is what your output of the vestigial sideband is going to look like. Okay? Any questions here? All right. So a couple more here. Let me see. What do we got? Okay, so determine VSB. So we have to figure out what the actual time domain signal is going to be. That's actually pretty straightforward. Okay? So we have 2 cosine waves. This is defined in terms of kilohertz. Okay? So we have 1 over 60. So these two, right, are going to make, so this is your output in terms of your vestigial. This becomes 1 over 8 because you have to multiply by 2, right? And then cosine 2 pi times 9.95k. First ones. The second ones, okay, you have a frequency of 10.05 kilohertz that are scaled by 3 over 16, so you have to multiply by 2. So you get 3 over 8. So 3 over 8, and this becomes cosine 2 pi times 10.05k. And then finally, you have these guys over here. It's 1 over 4, but you have to scale by 2 to get rid of that factor of 2 when you're modulating. So you get, not modulating, but when you do the transform. So you get plus 1/2 cosine 2 pi times 10.15k. And then you're done. Okay, so that's part B. Last one, guys. We're going to take this home. Show that M of t can be recovered using a coherent detector. Okay, well that's actually pretty simple. All you have to do is just apply, modulation and then do a low-pass filter, and then you're done. Okay, so you have your vestigial sideband coming in. Okay, you multiply by 2 cosine omega ct. Okay, and the output you put a low-pass filter, and then you get some version of the message that is scaled. Okay, so all you have to do here is you just have to shift left and right by this spectrum, and then you just add everything all together. Okay, so I'm going to do the first one where I'm going to take my vestigial sideband and I'm going to shift to the left first by that carrier frequency. Okay, so I'm going to do this one first. Okay, so when I do this, I'm going to take everything and shift to the right by 10. So in this case, you're going to get, so minus 150, minus 50, 50, 150. So that's, let's see here. So we have this guy, and this guy here. All right. So we have, let's see here. This is 1/4, 3 over 16, and 1 over 16 here. Okay. And then you have all the other ones over here, which I won't draw because we're going to apply a low-pass filter. So whatever over there. Okay. And now I'm going to take this signal and shift to the right by f of c. Okay. So what will happen is that you're going to get 2 impulses. So you're going to get 1, 2, and then 3 over here, right? So this is 1 over 4th, 3 over 16, and 1 over 16. This becomes 150, 50, and minus 50. This is in kilohertz. And then I have some other ones here that I don't really care about. Okay? And then what's going to happen is that I'm going to add these all up together, all right? So 1/4, let me see here. 1/4. So let me see here. So when I add 1/4 with 1, so 150. I'm just seeing what's happening here. One vestigial sideband. Oh, hold on a minute. So when I add these up, it should add up. So I have 1/4 plus this, and then 3 over 16 with 1 over 16. 1/4, 1/4 with, okay. So now basically what's going to happen now is that I'm just going to add these two things together, right? So when I add these two things together and when I do a low-pass filter, what's going to happen is that the output's going to look like this now. I'm almost done. So it's going to look like this. So when I add these two together, okay, so when you're doing the modulation, because this is what you're doing, so you're doing f of minus c plus, okay, and then you do a low-pass filter, your low-pass filter. Okay, so when I add these up, so we're going to have 1/4 at minus 150. Okay, so this is scaled by 1/4. Okay, and then when I take at 50, I'm going to have 1/16 plus 3/16. Okay, that's also 1/4. So minus 50, 1/4. And then 3/16, okay, plus, oh, sorry, let me see here. It should be over here, not at 150, sorry. So this should be over here, sorry about that. So you have 50, 3/16 plus a 16th again is 1/4. And then you finally have another one at 150 that's straight of 1/4 here. Okay? So this is actually your message signal scaled by 1/4. So therefore, the message signal is just going to be 1/4, not 1/4, it's going to be a half, right? Because remember, your impulses were scaled by a half. So the message signal, the output, right? The output is 1/2 m of t. because the original impulses were scaled by half. Because you have the 1/4 here, that's why you have the 1/2, right? Because the impulses are scaled by half instead of a fourth. Okay, and then you do a low pass filter and you're done. All right, so that's it. That's all I have today here. Are there any questions before we leave? You good? No? Okay, so that's it. So these questions, as well as the tutorial questions from previous, are all fair game. And yeah, so unfortunately I won't be here next Monday. I have to be out of the country for a professional matter, but the TAs will be here to invigilate. So yep, so just do these tutorial questions, take a look at the, you know, maybe some midterm questions from the past. There's an exam archive you can take a look at, and just watch the videos for the theory, and I think you guys should be good. All right? Okay, so midterm next Monday. I'll continue angle and frequency modulation on the Wednesday, and then we'll try to wrap up the course after that. Okay? So I'll see you next week. Oops.